How is the weather now, Kigali?
It's the rainy season here, so from time to time it rains a lot.
And warm?
Sorry?
Yeah, it's warm?
I actually don't know how long it lasts.
No, I mean, is it hot? Warm, hot?
Yeah. It's today it's like 22 degrees, so it's quite nice.
22, yeah, for me, so
Yeah.
it's fine.
It's just a lot of rain, but yeah. So people are starting to come in. We will be waiting for 2 or 3 minutes, then start.
Yes, don't worry, I have time. Yeah. I block everything for you. I just have. Oh.
So Fabien, do you want to take questions at the end or during or both?
Most at the end, but they can ask questions. Also, they can interrupt me if I have a very, very important question.
Okay.
Do you have news from Remy? Steve from time to time? No?
No, I called him a few times ago, but the last email I sent, he did not reply. So I don't know because he lost his email address and he was using the email address of his partner. So I don't know what happened, but I will try to contact him.
If you contact him and give him my greetings. Huh?
Okay, so we will start.
So how many people are present now?
23 for now, but they are coming in. So I will just start.
We can wait a little bit, don't worry. There's no hurry. I have a lot of work, but I block this afternoon mainly for you. So.
So, okay.
Olaya Olokombuyo. Kijama kireba nawe sha.
Good afternoon, sir.
Hi, Olaya.
I'm good.
Okay, so good afternoon, everyone, or good morning, depending on where you are located right now. So it's our pleasure to welcome Professor Fabien Gatti from the CNRS, the Centre National de la Recherche Scientifique in France. He's a research professor at the University of Paris-Saclay, working specifically at the ISMO lab. And Fabien Gatti has published more than 100 papers and already 3 books he worked on or edited around the topic of molecular quantum dynamics, studying spectroscopy, reactivity, diffusion on surfaces, quantum control, femto or atto laser pulses. Currently, his main topic of research is the multi-configuration time-dependent battery, and particularly is interested in a system of even larger dimension, and that are kind of challenging for traditional quantum dynamics. He's going to about this topic in the next few minutes. So if you can please mute your microphone during the talk, but he allows you also to interrupt him at various points of the presentation if there is something specific that you want to ask. Otherwise, the principal question will be taken at the end of this talk. So thank you for joining us, and we want to welcome now Professor Fabien Gatti for his seminar.
So first, thanks to you, and thanks to Steve and for the staff of the university for having invited, or the institute for having invited me. It's really a great pleasure for me to give this talk, your presence. So I'm a theoretician, and I would say that the goal of this presentation is mainly an introduction to the field of molecular quantum dynamics. So where we treat both electrons and the nuclei quantum mechanically for molecular systems, molecular processes. And so the main method I'm using is the multi-configuration time-dependent Hartree or MCDH method. So I'm one of the contributors of the MCDH high-level package. And I will give you some examples of applications. But I would say that the two main goals of this talk is first to show you that quantum effects can impact also the nuclei in chemistry, can have a strong impact on the nuclei, and it can be very important and very interesting to include these quantum effects in the simulations, which is also something which is not often done. And the second goal is also to show you that now we start to be able to treat rather large systems, because people who know this field in general, they think that we can treat very, very small systems. We have spent in our community on a lot of time on the H plus H2 leads to H2 plus H, for instance. And there are still people working on this kind of processes, or there are still people working on H2 plus, but I will show you here that we can go to much larger systems where we improve a lot, and even we can start to even study condensed phase. But here for this, we are really at the beginning. So as Steve said, I'm at the University of Paris-Saclay, the south of France, now is the biggest cluster of science in France. And I belong to the Institute of Molecular Sciences of Orsay, ISMO, which is, you have a lot of physicists, but also chemists. Officially, I'm a chemist, but I'm really at the interface between, I would say, quantum physics, more precisely quantum dynamics and chemistry, for quantum dynamics for applications in chemistry. So in molecular quantum dynamics, if you're interested, I've edited a book to show also a lot of applications for very important problems. So it's more like a book for other scientists, for coming from other communities. And here we treat again, so we make simulations where we treat quantum mechanically both electrons and the nuclei. I would also to mention the fact that I also published another book more for, I would say, for teaching, but sometimes at higher, at several levels in the book. But it's something that you could use because it's, if you want to teach quantum mechanics and illustrate also the concept of wave packet, the time-dependent Schrödinger equation. You know, in the courses of quantum mechanics, we don't give many, a lot of realistic examples of propagation of wave packets, and the book was here to present many realistic applications of wave packets. And there are in this book lab sessions using MCDH. It's very easy to implement on computers, and I organize lab sessions for students where they propagate wave packet on realistic molecular systems, where you can really compare theory and experiment, and you really see wave packets that have a real physical meaning. So where do we use a full quantum mechanical approach? And because we want to study problems for which quantum effects are very strong in chemistry, not only for the electrons, but also for the nuclei. It can be, of course, the quantization of the eigenstates. So, for instance, the vibrational eigenstates. So it's extremely important in spectroscopy, UV, but and also infrared spectroscopy. So it can be very important in astrophysics, or the spectroscopy of the atmosphere, and so on. So there is really people. Experimentalists really need spectra to interpret what they observe in the atmosphere of a planet, for instance. Another quantum effect is the presence of quantum resonances that can really completely change the reactivity of a problem. You can have a chemical reaction, and the concept of resonance is not quantum mechanical, it's classical, but here you have a quantization of the quantum resonances. And these quantum resonances can lead to very completely counterintuitive processes. For instance, if you want to, for instance, some of my colleagues have studied problems with collisions of molecules where the famous transition state theory used always in chemistry does not work at all because of the presence of these quantum resonances. We also study non-Born-Oppenheimer processes, where you have a very strong coupling between molecular electronic states. In general, when you have this kind of non-Born-Oppenheimer processes, you can have a lot of interferences between the components of a nuclear wave packet. And so even to calculate some absorption spectra, UV absorption spectra for some molecules, if you don't include these interferences effects, you will not reproduce the experimental spectrum. Of course, another quantum effect is tunneling. Here, tunneling is mainly for when you have an exchange of a hydrogen of atom or a proton. For more heavy atoms, tunneling in general is very, very, very small, because the tunneling, as you know, is linked also to the mass of a particle. But there are many extremely important chemical processes, even in industry, for which the limiting step is an exchange of hydrogen atom or a proton. Even also in biological biological system, in our body, you have also some exchanges of proton atoms that and you need, if you want to calculate just the rate constant of a reaction, if you don't include the impact of tunneling, you will get something which is a rate constant which is 10 times too small, because the tunneling effect is really very strong. Another quantum effect is the presence of also some quantum phase transitions. So here it's really very linked to also some important problems in physics. You can imagine, for instance, that some molecules are on a surface, a metal, for instance. Under some conditions, you can have you can create completely delocalized quantum state with very, very specific.
Hello.
Yes.
Hi, Gatti. Sorry to interrupt you. I think the screen is not moving because it's the same second screen, and I think that the mouse is you're moving the pointer. Seems as though there should be images.
No. This is normal. I'm sorry, I'm spending a lot of time on this first slide. I have just finished with this slide, and because this is very important. It's just this is a general introduction. So no, there's no problem. And another quantum effect is the presence of quantum coherence. For instance, if you excite a molecule with a laser femto laser pulse, or now atto laser pulse, and then you can guide processes by playing with both the quantum coherence and the quantum effects. Okay. So next slide. So see, I can switch the slides to one slide to another. So, but to solve the full quantum mechanical problem for a molecule is really very difficult. It's a very difficult task, because first you need what is called the potential energy surfaces. It is the potentials created by the electrons, and that create the forces acting on the nuclei that will make the nuclei move. And this must be first calculated. I'm not an expert of this. This comes from quantum, so-called quantum chemistry calculations, and the experts of this. And you need this first. And second, you need also to describe a system with sometimes very complicated coordinates of the nuclei. And then you have very complicated kinetic energy operators. These are something very technical, but extremely important. And at the end, you have to solve the time-dependent Schrödinger equation, or time-independent sometimes, but here we focus mainly on the time-dependent Schrödinger equation, and to have the quantum evolution of the system. So you need a numerical method to solve the Schrödinger equation, and you must understand that in molecular quantum dynamics, we have to deal with very, very strong correlation, much worse than in the case of the electrons alone. The quantum chemistry corresponds to the quantum mechanical treatment of electrons. The problem of correlation is very, very serious problem, but here it's much worse, since the nuclei are much heavier, and then you have much more correlation. So basically, if you increase the number of atoms, the number of degrees of freedom, the number of basis set functions increases exponentially, and you are very limited in the size of the systems you study. And the method, but we have improved a lot, and it's also perhaps very successful, if not the most successful method to solve this problem is the multi-configuration time-independent R3 or MCDH approach. Actually, there are several programs of MCDH in the world now, but the main program is the one developed by the group of Heidelberg, Germany, and they were the first, the pioneers in the field for MCDH, and they have a very specific philosophy and a strategy. And I've been working since my post a lot with Hans Meyer, who is the main developer of this package. He's a group of a famous Professor Zederbo, who is now officially retired or very active. Uwe Monteries also played a very important role, who was the first PhD student of Hans Meyer to work on MCDH. He has his own program now, which is very different. And I will also to mention Graham Worth also has also now his own program based on more which is and focusing more on photochemistry. Yeah. And so what is MCDH? So MCDH, in the MCDH, you have a wave packet. So here it will be, so you solve the time-dependent Schrödinger equation. So it means you propagate wave packets. So it's for the nuclear coordinates. So you have F nuclear coordinates to describe the vibrations, the motions of nuclei. And you see, you express in a basis set, of course, but you see something very specific to MCDH is that these basis set functions here are time dependent. Here you can, the capital Q can correspond to a set of coordinates, not only one, can be, let's say 1, 2, 3, 4 maximum. But they depend also on time. So you make a big difference. Of course, these time-dependent functions, which are called the single particle functions, are expressed in a time-independent basis set, a mathematical basis set, which must be complete, and which is what is called a grid representation often, or functions like the spherical harmonics or Hermite functions we see in quantum mechanics. But the problem is if you directly express your wave packet in this primitive basis set, the number of functions will be extremely large and you could not solve the problem. But the advantage, the fact that we use this intermediate basis set makes things much easier, since we optimize these time-dependent functions by a variational principle. We have a variational principle to be as close as possible to the solution of a time-dependent Schrödinger equation. So here you have some coefficients, some time-dependent functions, and they both depend on time, and they are both optimized by a variational principle. If you are a little bit familiar with the methods in quantum chemistry, it is really similar with to the MCSEF methods in quantum chemistry. These functions here play a little bit the role of the molecular orbitals in quantum chemistry that are also optimized by a variational principle. And these molecular orbitals are expressed in terms of atomic orbitals, but the number of molecular orbitals you need is much smaller than the number of atomic orbitals. So this can be seen like by comparison with the quantum methods in quantum chemistry as the MCSEF method, so highly multi-configurational, but the orbitals, if you want, are not for the electrons, they are for the nuclei, and they are also time dependent. So it means that they change in time, the active space changes in time, and then if we have a collision, for instance, you see that the optimal functions can be very different at the beginning, during the collision, or after the collision. So then you have a lot of flexibility. And in general, these numbers, N1 and P here, are much smaller than the number of primitive functions here. So you can treat larger systems.
Sorry, Fabien, I have a question.
Sure.
Little Q1, Q up to QF, how are they, what are they, and how are they different from big Q1 up to big QP?
So Q1, QF have, you know, the nuclear coordinates. Let's
Okay,
imagine
and then
each,
what about the big Q1?
so like, for instance, for water, it could be water will use the OH bond length,
Okay,
R1 and
okay.
R2, and theta the angle between the two to describe
What
the
about
equation.
big Q1 to big QP?
And here, just that you allow, instead of having just the one coordinate, it can be a set of coordinates. So it can be like, let's say R1 and R2 here. And here it could be theta. So here you can, instead of having, these functions are not functions of one coordinate only, R1 or R2 or theta, but they can be functions of two coordinates, like say R1 and R2.
Okay.
It's what we call mode combination. So these orbitals can depend on more than one nuclear coordinates only.
Okay, okay, thanks.
And we use this a lot to reduce. And now I'll show you a slide which is also directly linked to your question. You see here, I show you things with an example with three coordinates. It could be R1, R2, and theta. We have three nuclear coordinates. So you can express everything in terms of one-dimensional functions. So small q1, some q2, some q3. And then you express each function in the primitive basis set, but you have also the choice to include two coordinates in the single particle functions here. This is what I would call capital Q1, big Q1, and big Q2, because here you have two coordinates. Okay, so it can be a set of coordinates. So in general, we go to 1, 2, 3, 4, not much more for technical reasons. But then there is what is very nice if you do this also is that you are allowed also, for instance, if the function depends on more than one coordinate, you can express, instead of directly expressing this function in the primitive basis set, you can also use once more MCDH expansion, like with time-dependent functions for Q1 and Q2. And those functions here will be, of course, expressed at the end in the primitive basis set. So it means that you have here time-dependent functions of Q1 and Q2, time-dependent functions for the two together, and at the end you have the full MCDH expression. So you have more parameters that are optimized by the variational principle. It gives, so it's like in the variational principle, you minimize the quantity to be as close as possible to the solution. It's like having Lagrange multipliers in thermodynamics. And the goal, and here you give much more flexibility, and you can have a much more compact expression of a wave packet. The number of, if you use this expression here, the number of functions here will be smaller than the number of n1 times n2 times n3. Just to give you one example, imagine that you have the water dimer, two molecules of water. It's like making MCSCF contraction for each molecule of water first, with the first layer here, and then you add, so then you have something very compact for each molecule of water, and in the second layer, you include the interaction between the two molecules of water, and you do a new MCSCF procedure. So at the end, you will optimize all the functions at the different steps, and you can you get really a very compact form, and you can treat up to thousands of degrees of freedom. This is completely unique, probably the only methods that multi-dimensional where you can treat. This is something rather new. You can solve a time-dependent Schrödinger equation, even if you have some correlation with thousands of degrees of freedom. This part is what is called the multi-layer MCDH approach, where you re-express some of the functions also in terms of time-dependent functions. Okay, so you optimize, so like having orbitals, molecular orbitals, but then you have also molecular orbitals of molecular orbitals. You have many layers, and then at the end you get something extremely, you optimize at different levels the basis set functions, and you can treat very large systems. In the strategy of Heidelberg, there is still one. So you have to solve then very complicated equations of motion, and you have to solve them numerically. If you apply the variational principle, you will get this set of mathematical equations of motion, but then you have to also use integrators to solve them numerically. The people from my community, I would say my masters, like my PhD supervisor or my postdoc supervisor, who develop probably with all the integrators to solve the time-dependent Schrödinger equation. And 40 years ago, almost nobody could solve the time-dependent Schrödinger equation. So you have.
I'm sorry, Fabien.
Yes.
We can see the bottom part of the slide. It's because maybe you are not in full screen mode. It's like cut at some point.
Here, better.
Yeah, we didn't see that part. So okay. Maybe if you can try to go to full screen mode, it could be better.
It was full screen mode?
No.
A full screen. It was full. Sometimes full screen mode plus zoom makes some trouble. Here, do you see everything or not?
No, we can see the bottom part.
This is what, for me, this is just 1 minute. Ah. And here?
Yes, but no, we still can see it work.
You cannot see everything yet.
Yes.
But, I think it's not the first time I have a problem with Zoom like this. I will just move a little bit for each slide, okay?
Okay.
So you have to solve these equations of motion, but the number of questions is much smaller than if you directly try to solve the Schrödinger equation in a primitive basis set, so in a mathematical basis set, which is time independent. But you see, what I wanted to say is that here you have to build the matrix of a Hamiltonian operator. So imagine that you have 20 degrees of freedom. It means you have to have integrals with 20 degrees of freedom, and a matrix of a Hamiltonian operator with 20 degrees of freedom. So it's something impossible to store. And the strategy of a group of Heidelberg was to re-express all the operators in the following form as a sum of products of low-dimensional operators. Like here, it looks like one-dimensional operators. The principle is always possible mathematically, and the number of terms may be very large, but you can always have this expression. And then instead of having one huge integral, one huge matrix, you see a sum of products of very small integrals. Depends on 1, 2, 3 degrees of freedom normally, and this you can store them easily. But there is a lot of work to re-express. So in general, the kinetic energy operator has this form. So you don't have to care about the kinetic energy operator. It can be very complicated, but you have this form. But the potential energy surfaces that are provided by our colleagues in quantum chemistry are never, in general, they are never this form. And we have to re-express in a systematic way. And with this respect, measure breakthrough has been achieved recently, and we have now some tools to do it really, even for really large systems. It's really very new, and it's a very great progress. And we can treat now really large systems in a rather systematic way, provided that we have the potential surfaces. So let's finish with technical points, and I want to switch to some examples. And I want to start with some clusters. So here it will be Prudhomme water clusters, like so these are extremely water clusters, like water dimer, water trimer, and these here Prudhomme water clusters. Here you have, this is what is called the Zundel cation with 2 molecules of water and 1 proton. And here what is called the eigencation with 4 molecules of water and 1 proton. These kind of systems are supposed to be the most important forms when you have an excess of a proton. So this is really like but we want to describe the spectra of those molecules very well, and to have very good potential energy surfaces to describe them. Then, but it's not only to understand the spectra of those small molecules, because if you have very good potentials, it means that it can be used to describe really liquid water, solid water, or liquid water and crystal water when you have an excess of of protons, sorry. Because, for instance, for water, it is well known that if you can describe with a potential of water dimer, water trimer, it's enough to describe liquid water. And now in molecular dynamics, they do a lot of simulations, of course, in molecular dynamics in the field where they treat classically the motions of the nuclei. They use some potentials, but there is sometimes they are really questionable. We are not really they're not very reliable, and still a very important challenge to have very accurate potentials for these very important systems, so that at the end, people can do a lot of molecular dynamic simulations, but we are totally sure that there is that the potentials we are using for the basic elements of simulations are correct. So we did a long time ago with my colleagues from Heidelberg. We've calculated the spectrum of a protonated water dimer. You have 15 internal degrees of freedom, and this is a very, very difficult problem since there is a lot of anharmonicity. It's very, very floppy, and it's full of couplings between the modes, what is called Fermi resonances. And when a proton moves to one molecule of water, then it creates a pyramid H3O+, and then several motions are very, very strongly coupled. So if the standard methods, like the approaches, the perturbative approaches based on normal modes and quantum Monte Carlo methods could not reproduce the spectra here. It was necessary to use a full quantum mechanical approach, and we could reproduce what we did, my colleagues from Heidelberg. You start with a full vibrational ground state in 15 degrees of freedom. You apply the dipole moment surfaces on it, and you propagate it, and the Fourier transform of your autocorrelation function gives you the spectrum. And here I just show a zoom of one part of the spectrum. Here you have the energy in centimeters to the -1. And we had a most perfect agreement with the experiment for the very first time. These peaks correspond to modes that are very, very strongly coupled. To obtain such a, So to obtain such a very, very good agreement, and it means also that the potential and dipole moment surfaces, that depends on 15 degrees of freedom, are of a very high quality. Here they were provided by Professor Bowman in Atlanta, the US. And now we have a proof that the potential surface can be is really very accurate and can be used for many, many people who want to do simulations, even for example in molecular dynamics, to treat an excess of proton in water. Okay. And more recently, we did exactly the same, but with the second most important system, which is four molecules of water with 1 proton. So it's very, very new. So we had to and here we had to propagate with packets with 33 degrees of freedom. So again, it's extremely correlated and very, very floppy system. I just show you. So this is unpublished now. It's not published yet, but we have in blue our calculated spectrum, and in red the experimental spectrum. And now we are spending a lot of time to analyze this band here that corresponds mainly to the motion of a proton here. So it's very important to understand also the eigenstates that create this band, to understand how the proton interacts with the molecules of water. So basically, so the goal is and once you have we reach this level of accuracy, it means that the potentials are very accurate and that could be used. Now we have it has a really very general scope and can be used by many people, in particular molecular dynamics.
Fabien, can I ask a question, please?
Of course.
Yeah. Do you need all the 33 degrees of freedom to?
Yes, yeah.
You do. So is there an understanding of what are the correlations between these different degrees? Is it possible to reduce it to some combinations of modes?
But people of course try to really make a lot of it, but this kind of systems, everything is very strongly correlated. Huh? So now we are analyzing these correlations. That is what is directly linked to your question. For instance, here because here we know everything. Here you have very strong correlation between even the intermolecular motions and the intramolecular motions.
Right.
Because this is, is linked also to. So then you have to include everything if you want to get accurately the potential. So it's really extremely tough system.
Yeah. Thanks. And
people in my community, if not, people can get with much more approximate methods. But in our communities, our goal also to solve these kind of problems that cannot be solved with more approximate methods. So now we have also started with my colleagues from Heidelberg to the third and probably last very important system. With here you have a productive water dimer and 4 molecules of water. So here you have 51 degrees of freedom, and now it becomes rather system. I don't say not easy, but now rather fast to reach this kind of dimensionality. It's really very new, and to treat this kind of motions. I just also want to mention our work with Steve, since he invited me, and we are working together on the water dimer. So water dimer is smaller, but it's even more difficult because it's even more floppy. And you can be very surprised. There was even a paper in a good journal recently saying that the spectrum of a so important system, so small and so important system, because this was basic system to describe the hydrogen bond, which is at the origin of a very specific properties of water. We still don't understand. There's a lot of controversy about the spectrum in the domain where you have all the OH stretching modes involving the hydrogen bond. And perhaps here, so this is a collaboration with my colleagues from Dalian in China. The experimentalists have measured recently a new spectrum with a new and very powerful free electron laser. And they could only interpret, they have a potential surface with the 12 degrees of freedom, but they could not calculate the vibrational levels. And we still was started with MCDH to calculate it. And these are the first results obtained from Steve. And I just want to mention that this peak here, there was a lot of controversy, because for the first time, with a method based on first principle, based on first principles, we can assign this bond very clearly to this, the vibrational state linked to this OH bond, the one which is involved in the hydrogen bond. Next we'll work on the water trimer. If you have a good potential for water trimer, then it is well known that it is enough to describe correctly all the interactions in liquid water and solid water, which is not the case yet. They use models with DFT and so on, but this is still very questionable. So they made some approximations and we have no control. This is the goal of people like us to provide the very accurate potentials. Okay, let's switch to the next part. It will be shorter. I don't know how much time I have, but anyway, it will be shorter. So you see, this to give you an idea of what we can do with MCDH to treat rather large, it's really large for quantum mechanical approach, large molecules with very, very floppy, with a lot of very strong correlation, very strong interactions between all the modes. Can we treat even larger systems? Yes, I mentioned this multi-layer approach, and it's even possible treat really, now it's really very new we are starting to even to work with condensed phase with, for instance, to study biological systems. Of course, we don't want to reach the same level of accuracy as before, because here the system will be extremely large. For instance, I have studied this. So here is collaboration with a colleague from Orsay, Aurélien Lalande, who is doing molecular dynamics simulations with an expert of biological systems. And here you have what is called a cryptochrome system. You see, there is a big protein, many molecules of water. See, it is in water, the water solvent. And you see there are small molecules and in the protein, and if there is absorption of light, then you have a cascading of electron transfers. And so there are many non-adiabatic processes. So just for to justify a little bit, but process, it is well thought that this system of cryptochrome are in the eyes of the birds, of some birds. And you know, when you have this process, absorption of light, it creates an electron hole pair in the eyes of the birds, and it creates a small magnetic moment. So that, depending on their position, the position of the birds with respect to the magnetic field of the Earth, they don't see exactly the same thing, because the magnetic, because there is a coupling with this small magnetic moment in their eye. So this is perhaps an explanation for why some birds can migrate and go to the south or to the north, depending on the season, because they don't see exactly the same thing. Perhaps it's darker in the south and lighter in the north, and they find their way during the migrations. But okay, I'm not a biologist, so it's just and but just want to say here that it becomes possible to converge the quantum dynamics of systems of this size. Here you start from an electronic ground state. When there is in the experiments they use a laser, they excite one electronic state, and then you have several electronic states that are coupled. And you are cascading of non-adiabatic processes and electron transfers. And in our first study, we just studied the transfer from this state to that one. And Aurélien Lalande did some, so in this case, no, just, yeah. And you have here just I show the time constants for the electron transfers between the two different electronic states. First one is very fast. Second one needs between 4 and 15 picoseconds, and then it becomes even more slowly. Actually, we must interpret with care these experiments because it's difficult to distinguish the different steps. But anyway, what I wanted to say that with molecular dynamic simulations with a constrained DFT approach, Aurélien could propagate, not propagate, but make a simulation of a system with classical mechanics for the nuclei for a given temperature. And then he can get a spectrum. You Fourier transform the autocorrelation function. And this is something rather technical, but you can discretize the spectrum and then extract some normal coordinates, some coordinates of the nuclei. And from this, and you can also create a model with two electronic states that are coupled. And you have one huge bath of nuclear degrees of freedom for each electronic state with a coupling between the two, which is here taken as constant. This is what is called spin boson model. Perhaps some physicists know this. We could improve a model because here it's rather simplified to just take a constant between the electronic states, something we could improve in the future. But anyway, with this spectrum, we can extract some, discretize the spectrum, extract some nuclear degrees of freedom corresponding, each frequency of the nuclear degrees of freedom correspond to the values that are here in centimeter to the -1. And the heights of a peak will give you the frequencies and also the coupling between the modes. And actually you have 110,000 atoms. So in principle, you have 330,000 nuclear degrees of freedom, but we don't take everything. What we do is just we discretize. We take at the beginning 50, then 100, then 200, and we do the dynamics. And we see if the dynamics does not change anymore. And if it does not change anymore, it means that we have enough nuclear degrees of freedom. And we went up to 1,000 degrees of freedom. We could converge. It's really highly correlated. It's not just a Hartree approach. There is there is really some correlation with this system. But with, so we could converge such a huge calculation up to 1,000 degrees of freedom and converge the dynamics. And of course, you have to believe that this, we could converge the dynamics. So we converge very carefully the size of a basis set, which is huge, since you have many degrees of freedom. And also with respect to the number of nuclear degrees of freedom you take in the model. So the quantum dynamics was converged, but then the validity of your calculation depends on this model here you gave as an input coming from molecular dynamics simulations. But the quantum dynamics itself is converged. I think it was the first converged calculation for biological systems with full ab initio method. It's not the last one, but now it becomes possible to treat even biological systems. Of course, you have to believe that the molecular dynamics simulation with constraint DFT or TDFT are sufficient to describe these non-adiabatic processes. We could even thermalize the system. There are many options in MCDH. You can do a lot of things. In particular, you can thermalize also the system. And you can get here, I give speed of a transfer in for given different temperatures. And the end we get something which is close to the experiment. And what is important to see here is that we have, with this approach, we have the full wave function. So it means that we could also, we can have access to the quantum coherence. I mean the electronic quantum coherence, the coherence between the electronic states, and also the vibrational coherence. And I say this because this is something very important. There is a lot of works and a lot of controversy about the role of quantum effects in biological systems. And some claim, in particular in photosynthesis, some claim that if photosynthesis is so efficient to transform light into chemical energy, it is because photosynthesis uses some quantum effects, some quantum coherence effects that would explain this so efficient process, and also the fact that the processes are extremely flexible. They don't depend on the fluctuations of a system and of your environment. So in principle, now we have a tool to analyze the nature of this quantum, this coherence, because there are a lot of discussions if coherence is really quantum mechanical or classical, or if it's electronic or vibrational or vibronic, and so something we could now probe with MCDH. And in terms of applications, if we can, if it is true and we can learn to use these quantum effects, we could also improve a lot the photovoltaic systems, because the photovoltaic systems are not efficient at all. And if you have any defeat or any fluctuation, in general they break. So we could try to propose new photovoltaics that would be much more robust and much more efficient. Okay, and I conclude with just some perspectives, since I know that people are working in condensed phase or on molecules on a surface. So I don't have to show you many results because I have things that are really in progress. I'm working now on a PhD now in on the reactive scattering of ammonia on a surface of nickel on a metal. And then what happens is that when the molecule of methane comes close, then you can break the CH bond. It's something very difficult. This step is the limiting step of some extremely important chemical processes in industry, the production of H2, for instance. Because to break this CH bond, you need a lot of energy, and this way you need a catalysis, which is here this metal. And so this is a collaboration with WAGO, who provided us some very accurate potential energy surfaces. But his problem is that he cannot treat everything in full dimensionality, and he asked us to try to calculate the cross sections of the reactivity in full dimensionality with MCDDH. And we have also a colleague with an experimentalist in Lausanne who does very nice experiments where he excites some very specific modes with a laser. Can excite the stretching modes of vibration, the bending modes. He can even excite the rotation of a molecule and see the impact on the cross sections, if he enhances or not the chemical process. And then it is a very detailed understanding of this elementary process at the quantum level. And the goal would be, if we are in full dimensionality, to reproduce the experiments on Rheinerbeck, and then we could have a really very deep understanding of this elementary process, which is again the limiting step for an extremely important process in S3. There are other examples of like this. Another project is also the creation of, here not the destruction of a CH bond, but here the creation of a CH bond with a hydrogen atom on a surface of graphene. This is here a collaboration with Alex Vodke, who is an experimentalist from Göttingen. He did the experiments. He has some reaction probabilities depending also on the angle of the colliding hydrogen atom. And he has a colleague, a theoretician, who does classical simulations, but the experimental and theoretical results do not really match, and he wants to see if it is due to the quantum effects. Hydrogen creates a lot of tunneling effect, as I told you at the beginning. So this is really part of our collaboration to include everything quantum mechanically, to reproduce the cross sections and to see if we arrive to reproduce the experimental data. Here you see it's a really difficult problem, because when the hydrogen atom is close to the graphene, then all the carbon atoms start to move, and the frequencies of vibration also change. So you cannot treat the graphene as just a harmonic bath. To include the harmonic bath in MCDH is really easy, but here you have to include the motion explicitly of all the carbon atoms in this unitary cell, serving periodic, and you have to include everything, and you cannot make an harmonic approximation. So this is again work which is in progress, but now it becomes doable. Even 5 years ago, 5 years ago, to study this in systematic ways was not possible. And to conclude, I would just want to mention very briefly that also I'm working a lot on the diffusion of molecules on surfaces, because in group of Professor Ellis in Cambridge, we have developed this what is called the helium spin echo spectroscopy. So I'm not really an expert, but they send some helium atoms on a surface, and they can get some information about the diffusion. Then there are molecules on the substrate that are moving, there's a diffusion, and they can extract some the diffusion rates. Well, they claim, because the interpretation is still not something we're not sure that it's very clear, but they can get a lot of information about the diffusion rates depending on the momentum transferred by the helium atom to the molecule and depending on the direction, on the crystallographic direction. And then it gives a lot of information about the topography of the surface, because it will completely depend on if you have a barrier or not, and so on. So you can explore all the topography on a surface. And we have started to develop a systematic study of this, but with a quantum mechanical approach, particularly for hydrogen atoms or H2 is really very, very well justified. We have some potential energy surfaces. Again, it's always the limiting step. So you have here is hydrogen on palladium here. So you have to define a cell and very specific topography. In general, what we always do is we calculate some the first vibrational states to compare with spectroscopic data. And the agreement also is very good tests for the quality of a potential surface. And we start to have some diffusion rates. Depending here, you have a crystallographic direction. Here, this is the momentum transfer from the helium atom to the particle on the surface. And in solid and dashed line is the difference between solid line is the full calculation, in dashed line is when we try to remove the tunneling effect. We did it in a rather artificial way, but you see that the tunneling effect plays a very important role. Here you have for both two different temperatures, and here is for another direction. And we had some first also values and some comparison with experiments which were good, but here also we had to include some friction. Because when the molecule is moving on the surface, of course, there is some friction. The main origin of the friction is the presence of the electronic states, the continuum of the electronic states of a metal. And then you can create some electron-hole pairs, and they create some friction. And now, here we have included them in a very ad hoc way by actually we chose a parameter, ad hoc parameter, and we chose a parameter so that we can fit with the experiment. So it's not very, very, very proper. But now some of my colleagues were now trying to include in a really in a very purely first principle approach, the Lindblad approach to include the friction with ab initio calculations for the coupling with the electronic states of the metal. So here I show this is not for one. This is here for this is the diffusion rate of here it's CO. I guess this is C. Well, no, it's hydrogen on palladium. So this is the calculation as a function on 1/T. T being the temperature in Kelvin. This is the full calculation here without tunneling. You see it's very different, except if you are very high in energy for temperature. And here it's what is called a Wiener treatment, which is very approximate treatment, but very, very often used. And you see that doesn't work. So you really need a full quantum mechanical method. That's it. So for this part, again, I repeat that for the diffusion of molecules on surfaces, we go one step further by including by ab initio calculations the friction and to see the impact of friction, but on the diffusion of the molecules on a surface. And as a general conclusion, you see that we have a very powerful tool, MCDH. We can be used for many different kinds of simulations. I didn't show, for instance, I'm working a lot on coherent control with laser pulses. It can be femto, atto pulses, or you have, can be used for many systems. I would say that, so it can be used for many systems. It doesn't mean that it is optimal for many problems, even problems including quantum effects. MCDH is really very efficient, really optimal, I would say, if you have a strong quantum effect, but a fast process. Because if the process starts to be really very slow, you will lose a little bit of the advantage of using MCDH. This is true for any time-dependent method. If it's very slow, you will have to propagate during a very long time. So for instance, for ultra-cold chemistry in general, they use time-independent methods, but they are very limited in the size of the systems. Time-dependent methods, it's difficult for time-dependent methods to be to treat slow methods, and for MCDH even more true, because if it is fast with this, this variational approach, it means that with a few configurations in general you catch very fast the quantum effect, and then you don't need to expand, you don't need to use a very large basis set, and you can treat very large systems. But if you want to propagate on a very long time, then you will need many configurations, and you will lose the advantage of using MCDH. Another point, of course, is the limit, is what I write here, is the necessity to have a potential energy surfaces. So I need quantum chemists or people from doing molecular dynamics. We depend a lot on them, and also in a form adapted to MCDH. But what I explained at the beginning, this sum of products of low-dimensional operators. But this part almost now is solved, because and it's rather recent. Now we have something systematic. So the main problem is always to have first potentials. And to be aware that we also use sometimes MCDH as a time-independent method, not extremely efficient, but we can calculate eigenstates, so quantum resonances, if the system is not very large. And since probably most of you are physicists, I want also to mention the fact that MCDH is more and more used to treat fermionic and bosonic systems. I have, for instance, my colleagues Peter Schmelcher in Hamburg, or Ophir Alon in IFA, or Axel Lode. They have extended MCDH by symmetrizing or anti-symmetrizing the wave function to treat bosonic and fermionic systems. And they're doing a lot of studies on the behavior of fermionic and bosonic systems. And the advantage of MCDH is that at least under some specific conditions, you can treat much larger systems. So this is really pure physics, for instance, to study Bose-Einstein condensates. That's it. So I would like to thank several people. Steve, so I've been working with Steve. Now he knows, I think, to use MCDH better than me, I would say. That's not a joke. And I would also to thank, of course, my colleagues from Heidelberg. Hans-Dieter Meyer is really the main holder of the program, and I did my postdoc with him and Heidelberg, and since then we have been working all the time together, and we are very close to one another. Oriol Vendrell, who is the new professor in Heidelberg, and very strong collaborator. It's very good news. He got the position of professor when the famous Professor Zederbaum got retired. So, and he's working a lot on MCDH, so we collaborate a lot together. Markus Schröder, who developed this a new method to refit the potentials, which is probably a major breakthrough. Since what I said before, now we have systematic ways to express, even for many degrees of freedom, to re-express the potential energy surfaces. David Mandivet was my former postdoc who did the work on the biological system. Now he's postdoc in Heidelberg. In Orsay, I have my colleagues David Lauvergnat, Daniel Peleas-Ruiz, who's using also MCDH a lot. And for the part on the diffusion, Roberto Marquardt and Jean-Christophe Tremblay, my colleagues from Strasbourg in France. And Jean-Christophe is really the expert of to include the impact of friction and due to the continuum of electronic states in the metal. And I would like to thank you for your attention.
Okay, thank you, Fabien, for your talk, and
it was long.
thank you, everyone. Thank you, everyone, for attending. So now we have time for some questions. So if you have any question related to this talk, but even maybe related to the MCTDH method, if you want to know more, you can ask a question.
About the field, huh?
Yeah. So he's probably one of the best person to answer your question right now. So the floor is open. Either you can write your question on the chat, or you can unmute yourself and ask your question.
Yeah, Fabien, please, I have a question. Thank you for the talk.
You're welcome.
Yeah. Is there a systematic way to include temperature effects in MCTDH?
Now, temperature, yes. David Madivetapia, when he was my postdoc, he has including, there's a way to thermalize the system, and now there's an option, it is in the official package. So now, yes, it is systematic. You can include in systematic way the temperature, yes.
So that's by coupling it to a bath, or because you see the Schrödinger's equation, if you change T to tau, then you can include temperature, or how does he do it? He couples it to a bath.
So when we are talking about temperature, it can be the temperature or something, or everything or some parts. Huh?
Okay.
So you can thermalize everything if you wish, huh?
Okay.
But you can also thermalize just one part. And
okay.
I don't know, depending, well, you can thermalize just one part of the system if you need, because sometimes you have just, for example, a very cold temperature. I know that sometimes there are some temperature, but just for one part of the system. So there's the possibility to thermalize some parts. So actually, in concrete terms, you will thermalize one part of a Hamiltonian operator, but you can also thermalize everything. It can be expensive. Sometimes it's expensive to thermalize, but because how we thermalize, it works well, but it's not so efficient, not very fast. But you can thermalize the full system on one part of the system.
Okay. Thank you very much. There's a question from Uriel Morzan, and then a question from Ali Hassan Ali. So Uriel, you can unmute yourself and ask.
Yeah, thank you. I thank you for your talk. It was very nice. I have a question. I didn't fully understand in your spin boson model.
I was very fast.
Sorry?
I was very fast. I didn't.
Yes, I don't fully understand what exactly do you get from the spectrum. Which information to which parameter to the spin boson model do you get from the spectrum, and what is exactly your bath here? By use of environment.
Of course, to explain this, it could take a long time. I completely agree. It's not actually we did many things. So I'm not going to explain everything in detail because I have to show you all the equations. But you see here, what we do is we do the molecular dynamics simulation in one diabatic state, for which you have is thermalized, and you have one very clear functional for because we are using constraint DFT. And from this, you get the heights gives you some information about. So here, what is here? Here it corresponds to the frequencies of the coordinates. We're using normal, actually we're using the normal coordinates of the electronic ground state. The use of normal coordinates for such a problem is questionable. It's not very, because we know that the modes with very low frequency plays a very important role. So in the future, it will be important to add more harmonicity, but this is something we knew from the beginning. So what we do is we discretize this part. Let's say we take 10. You take 10 with the same difference between. Then you get 10. It's like you get 10 normal coordinates, and then you have the frequency. The 10 normal coordinates, and the height of the peaks. So something not obvious. I have to show you. I need to show you the coordinates. It will give you also this some information. There is a relationship to give this the coupling of a bath with of a mode with the rest. It's not something obvious. I have to show you the equations. And you do the same for the over electronic states and the energy. And Aurélien, thanks to the fluctuations between the two, can get the coupling between the two electric states. It can get some information about the energy difference between the two electronic states and the coupling. So what we do, so you extract from this. So it took us a long time to do it very well. It's not something obvious. I learned this. Actually, the expert was Michel de Souter-Lecomte here, which is here, and I learned with her during this collaboration. And what we do, we extract, and then we, instead of taking 10, we take 100. Then we take one, we'll discretize and take 100. So it means that we first do a dynamics with only 10 normal coordinates. You have here a model with 10 normal coordinates. The frequencies correspond to the values here on this axis, and these parameters here are linked to the heights of the peaks in the spectrum, the heights of the spectrum. So there are equations that I have to show you, and again the coupling between the two electronic states linked to the variation of the energy of one state to the other compared to the other. So here you do the dynamics with 10 states, with 10 normal coordinates. You get a value for the transfer of the electron, and then you do the same with 50, and then you get something different. So then it means that definitely 10 were not enough. So then you do the same with 100. We discretize with 100. So I start to have a bath with 100 modes. And then I compare the dynamics between 50 coordinates and 100. And then I get something different. And then you do this until it is stable. Actually, we went up to 1,000, but this part doesn't play a very important role. If you remain only in this part, 250 is enough. And with 250, if you discretize more, increase more nuclear degrees of freedom, you get the same value. So you know that it was enough it was enough to take 250 normal coordinates to converge the dynamics. And the maximum possible, since there are 110,000 atoms, the maximum number of coordinates that we didn't reach would be 3 times. So that is 330,000 nuclear degrees of freedom. This is really all the coordinates describing the motions of the protein, the molecules, and the molecules of water.
I see. And at the end, what you get is the rate constant for electron transfer.
Yes, and not only this, we could get also the electronic coherence between the two. Here, the electronic coherence, to tell you the truth, was small, because the coupling here is small, so it's not a problem with the strong quantum effect. But we have access to all the wave function, and then we can define, so always a little bit artificial, to define because it's always related to a model. For instance, the electronic quantum coherence between the two electronic states, the coherence between some vibrational states, and so on. And but here it was very small. But many people claim, that's what I explained, that for some very important biological systems, this quantum coherence would be extremely strong and would explain why, for instance, photosynthesis is so efficient. Bon. There are people who don't believe it. There are people who say this is a classical coherence. There are people who say this is not electronic coherence, this is a vibrational coherence. There are a lot of controversy. There are people who strongly believe that there are strong quantum effects, and that this is in particular electronic coherence, that biological systems can keep during a long time, let's say 100 femtoseconds, a strong quantum coherence between electronic states. But nobody, until now, nobody, they use for the theoretical simulations, they use very simple models, so they get a little bit what they want to look for. So here, but with this tool, perhaps we could decipher the problem and explain if we can work with the experimentalists to see if we can get, if there is really strong quantum coherence and the nature of this coherence. And even more, if we could use it to, if it's true, if it's quantum mechanical, and if we can use it to design new molecules, for instance, new photovoltaics, that optimize this quantum coherence to improve a lot the efficiency of photovoltaics.
Thanks a lot. Much more clear now.
So there's a question from Ali. Ali has a question.
Yeah, thanks, Steve. So thanks, Fabien, for this very interesting talk. I really enjoyed it. So, you know, I'm very interested in this Eigen and Zundel stuff because it's something that I've been working on for a while, but from, of course, from the perspective of the poor man's ab initio DFT perspective. You know, this whole field started off with, you know, some of these simulations that, you know, Mark Tuckerman and Pernello did 30 years ago. And this sort of motivated new experiments in the condensed phase by Andrei Tokmakov, Dor Ben-Amotz on IR, you know, time-dependent IR spectroscopy of the excess proton in water and also the hydroxide ion in water. So on the one side, there are now all these very interesting condensed phase measurements of the time-dependent spectra as a function of concentration. This, for example, as a function of concentration of pH. And I wanted to get your perspectives on whether you think in the near future it's possible to make one-to-one comparisons with the condensed phase IR and Raman spectra that have been measured. So that's the first question. And a related question is, you know, one thing that's also been measured experimentally from NMR back in the 60s are diffusion constants of the excess proton and the deuteron.
Yes.
Yeah, what are your thoughts on being able to get a handle on those predictions to compare with the experiments with MCT? Yeah.
On short term, I don't know. So because I have in general people who are working on this. There's a group in the École Normale Supérieure in Paris of theoreticians who are working a lot on this, I guess.
Yes.
And they use more. They invited me, by the way, not a long time ago, to present this work. And I think they are working on these kind of things, but they're using more DFT, and the electrons are treated quantum mechanically, but the nuclei are treated classically.
Right.
Yeah, and they get already, I think, a lot of very important information.
Right. No, sure.
Yeah, and well, I cannot, I don't know if we can do on short term. I don't know if we can do quantum mechanical simulations for this. Perhaps on long term.
But for example, you showed these QMMM.
Yeah. But I guess if they provide us, yes, what I say is not completely. There is some hope. I'm more a chemist, so I really some hope that at some point we could even describe the dynamics on with a little bit models like what I said for the biological systems, and to the main problem. I'm not against nothing against DFT.
Sure.
A general potential. And if we can rewrite everything in a form adapted to my program, perhaps we can do some quantum dynamic simulations. Yes.
Yeah. Okay.
This is
Can I, Steve? Can I ask another question, please?
Sure.
Okay.
Sure.
So Fabien, I have another more maybe philosophical and provocative question, which is so I'm an outsider to quantum dynamics in terms of the method development. But what MCDTH versus RPMD? The formalism of David Monolopoulos for quantum dynamics.
Can you repeat again? I know him very well. Because I don't have, sometimes I don't have.
So the alternative to doing quantum dynamics,
yes,
is green Kubo type correlation functions that you do with ring polymer path integrals.
Yeah, I see.
So is there I guess is there a limit? So if you
finish please.
No. So I guess is there are two questions from a theoretical side. Where do these two things, when are they the same and when are they different? And then from a practical side, has anyone done a systematic comparison of the two approaches to see what the differences are on like simple systems?
For this system, I cannot, for this method, I cannot really answer really very precisely, but there are many methods, of course, alternative methods, like also path integrals and many strategies to treat much larger systems, including the quantum effects. In general, I would say the main problem is that more approximate.
Sure.
So they're more approximate, so they can get a lot of very important things that anyway we cannot get because they're simply still too large even for us. So, and like for example, for path integrals, of course there were some comparisons.
Yeah, sure.
They can see that where they see some limits, or sometimes they have a good agreement and so on. But I would say MCD. So that many. To me, it's more complementary.
More
complementary, but MCDH is supposed to be at least this in our community. With first, we give really the benchmarks to have really very converged quantum calculations that can be used to compare the more approximate methods.
Yes. No.
So, and then of course there is a lot of future for the other methods, because in any case they will in chemistry they work with so large.
I mean, my reason for asking was thinking of a way where I could imagine where if one could do really accurate MCDTH on a small subsystem, then in a region around it do RPMD in a way to couple these two worlds, right?
Actually, we are thinking of a lot of this kind of strategies. So to try to have
very good.
One core, but it's always a little bit delicate.
Yeah, no, I imagine.
Because the interface you can lose also. You must be very careful. It's possible.
Sure.
It can be. There was a lot of work interface, because the danger, for instance, many people started with a quantum core with a classical environment, for instance. But then the main problem is the interface. You completely lose information about the quantum effects at the interface. So you have to find clever ways. I saw some works. I'm not an expert of this, but they treat one core in one core very accurate, and then the rest less accurate. And I think this is in the case a very good strategy on the long term. But be also aware that it is also the case for MCDH, because MCDH itself converges very well, but the potentials we use.
Sure. So
then we do the same, because for one core sometimes we try to be very accurate for the potential, but for the rest, for instance, we can just have a device, just a huge bath, and which is much more approximate. So we also do this kind of little bit of strategies, not because the potential, we cannot have a very accurate potential that guarantees a perfect description of all the quantum effects due to the potential itself.
Yes. No, thanks. Thank you very much. Thank you.
Okay, there is an additional question from Jean-Paul Kuranga. I don't know if he's still there and if he can unmute himself and ask his question. Instead, Jean Bosco Kuranga, if he's here.
Yes.
Yes.
Thank you. I was asking my question was related to that can DFT method be used for deciphering transfer proton in gas phase as well as quantum actual solution?
Excuse me, the sound. Can DFT be used for?
He actually
DFT methods.
Yes.
Used for deciphering, transferring proton in gas phase and quantum actual solution.
Did you hear, Steve?
Yes. So he wrote his question on the chat. He said, can DFT method be used for deciphering the transferring of proton in gas phase and continuum aqueous without intervening Born-Oppenheimer molecular dynamics? I don't know if you can see the question.
You have to, so, you know, okay, I can close. Yes. Can DFT method be used to the transferring of proton gas phase and continuum aqueous without intervening? If it's related to two things, if it's related to the problem of the clusters of water and protonated water, because the protonated water there is a proton transfer. For this part, I guess DFT is not enough if you want to reproduce accurately the spectra I showed, because they are very accurate. But if you are talking in general about a transfer of proton in gas phase, and I guess DFT can give some results, yes. But it depends on the accuracy you want to reach. For the clusters of protonated water dimer, for instance, to reproduce the spectra, and in particular to describe very well the proton transfer between the two molecules of water, for sure, I think here you have to go to a higher level of accuracy than DFT.
Okay.
But DFT can be used perhaps for other problems for proton transfer.
Okay. I don't know if this answers your question, Jean Bosco.
Yeah.
Okay. Is there any other question in the panel among participants? Like I said, if you have even a general question about the MCTJ method, this is probably the best time to ask it. Otherwise, we may end. Okay. All right. So since there is no more question, I will just take this time to thank Fabien to spending so much time with us, and hopefully next year when everything will open, he will be able to visit our institute here in Kigali. We can have more discussion about all of these topics. So thank you all for attending this seminar. I saw many people coming 1 hour after. I guess it's the time difference that was not very clear. So I will try to make it more clear the next time. So thank you all for attending, and thank you to Fabien.
Thanks
I'm going to end
for having invited me. It was really a pleasure.
Yeah.
And I really hope that I will come to Kigali soon. after the pandemic.
Yeah. Okay. Thank you, everyone.
Thanks a lot.
Thanks, guys.
Thanks. Goodbye.
Thanks. Bye.
All right.